the last talk in this session. I'd like to introduce Professor Pitoura from the Computer Science Engineering Department at the University of Ioannina, who will talk to us about managing big data graphs.
Good morning, everyone. Thanks for the invitation, Kostas. My talk today will be on how to manage big data graphs. This has been a very active area of research for, let's say, at least the past 5 years. So there's a lot of work being done in this area. And this is the questions I will try, the 3 basic questions I will try to address in this talk. So why, what, and how? Why graphs? Why should we care about graphs? Why are graphs important? And then what? What type of analysis should we do on graphs? And then how? What are the systems and the tools that we can use to analyze graphs? Okay. So as I said, this is a very active area of research. Too many papers, too many good work, a lot of good work being done in this area. So this will be just a broad overview. I will not cover everything. I will not cover anything in depth, but it will give you a nice overview, I believe, about the area. Okay. So let's start from why, the motivations. Why should we care about graphs? Anyway. So the main motivation behind most of the recent work in data graphs is social networks. You all know about social networks. Most of you use at least one of them. Facebook, Twitter, LinkedIn are some of the most popular ones. There are billions of users, trillions of connections, a lot of money being made in this area, and a lot of fun things to do with this data. Okay, so social networks, the underlying model of social network is, of course, a graph. Okay, so the node is the user, and the connections are either the relationship, represent the relationships between the user. So, for example, in Facebook, a node is a user, and then a connection, an edge, represents the fact that 2 users are friends. The edges can also play the role of modeling the interaction. So we can have an interaction graph where, again, nodes, users, edges represent the fact that 2 users interacted with each other. And this is a more dynamic graph. Now, these graphs can be directed or undirected. For example, Facebook is modeled as an undirected graph because the friends relationship is undirected. Twitter is modeled like a directed graph because the follow relationship is directed. You can follow someone, but he does not necessarily follow you back. Okay, so we have both directed and undirected graphs. We have dynamic and less dynamic graphs. And besides social networks, we had graphs before, and we still have large communication networks. So graphs model communication between people. So nodes are people again, and the connections represent the fact that people exchange emails or phone calls. So we can get data in the form of graphs from communication networks. And of course the internet. The internet is again a huge graph. The nodes are the internet nodes, and the edges represent communication between the nodes. Financial networks, where nodes are companies and the edges represent relationships between the companies. Biological networks, nodes are proteins, edges are interactions, nodes are enzymes, and edges are chemical reactions. And of course, one very popular and very important graph is the web. Okay, so you do have nodes. Now these nodes are web pages, and the edges are the links between the web pages. And then there are more graphs. So there is the link to open data, there is the food web, it's what, some less popular graphs. And then there are graphs that you can find in many areas of computer science, like information retrievals, where nodes are documents or terms, and the links represent the fact that a term appears in the document. Okay, so graphs are everywhere, and then just a small note about this kind of graphs. This kind of graphs are not random. So graphs that model natural networks are random in the following sense. They are what we call scale-free graphs. This means that their degree distribution follows a power law. In simple terms, it means that some nodes are very popular, they have a lot of friends, they have a very large degree, but most nodes are less popular and they have small degree. And in mathematical terms, this is expressed with a power law function, which if you plot it in the log-log scale, it gives you this linear form. Okay, so one thing about these networks is that they are not random. Okay, the other thing is that they also have what we call community structure. They are clustered. So we tend to find small communities. Think of Facebook. There are small communities of people which are friends with each other. So they are not random graphs because of the power law. They are not random graphs. We follow communities. And the third fact is that these tend to be small world graphs. I will not get into the details of the small world graph, but the idea is that the diameter, the maximum distance between any two nodes, is really small. I don't know if you have heard about the 6 degrees of separation, please. Actually, it means that if you take two random people, they are all connected through common friends or common people they know. Okay. So between you and everyone else, there are limited people that you know and can get you to the other person. Actually, it's for a social network, the number is even smaller. For example, for Facebook, the diameter is around 4. So this is a very connected world after. Okay, so we have large graph, we have graphs which are have particular properties that we can study. And then, okay, we have the graphs. How can we use them? There are many applications and a lot of information in this kind of graphs. For example, we can use the graphs, and the graph structure is used to rank information. One of the most important algorithms used in search, for example, in Google, it used to be page rank. So you rank the importance of the node based on its popularity, on its number of connections, of how many other important web pages point to it. So the structure of the graph is very important for us to rank information. It's also important to identify influential people, to find communities, model complex dependencies, make meaningful recommendations. Nowadays, recommendations are based not also on what we do individually, but also on what our friends do. So things that our friends like or people similar to us like are recommended to us. So the graph structure plays an important role in recommendations, also in prediction, in understanding information cascades, how information flows in the graph, how does a video get viral, and to understand how news propagates or how diseases propagates in other kinds of networks. Also in event detection. Now events appear more quickly on Twitter than in traditional news media. Okay. And then we have applications in computer security and so on. So graphs are important. We have graph data. What to do with them? What are the kind of analysis that we can do on graphs? Okay, what kind of analysis? Well, the thing is that there are no core operations. Well, in databases, we know we have SQL. Okay. Here we don't have a specific kind of analysis that we can do in graphs. So a rough classification can be the following. We have offline graph analytics, so we get the graph and we try to find information from it, like count triangles, which is sounds strange, but it's a common operation of graphs because it represents friendships. And then do clustering, community detection, page rank, betweenness. Okay, so one type of analysis we do in graphs is offline analysis. The other kind of analysis we do is online analysis. So in this case, we have these huge graphs, and we ask queries, and we want to find specific information in these graphs, and we ask this. We express this through queries. Again, even in this case, there are not specific any core operations or any core queries, but we can divide them into flexibility or distance queries, where you want to find the distance between two nodes, and the other is graph pattern queries. So you have a small subgraph, and then you want to find if information that resembles subgraphs exists in your huge graph. And then there is SparkQL. We have some experts in RDF here, so there is also SparkQL. And okay, so we can talk about offline and online, but this is not the only thing that we can do with graphs. Then there are other things like modeling, trying to find a model that to generate a graph and predict its evolution in the future. There is very nice work being done on visualization, that these graphs are really huge. So to find out information about these graphs, you need to find some way to represent it visually, to make it more easy to understand. And then there is interactive exploration, and so on. And yet another way to distinguish between the different ways to operate on graphs are global operations. Well, you need to traverse the whole graph, and there are node-centric or microscopic ways to look into a graph, where you want only to have access to the neighbors of a node. And then my final distinction is based on whether we use only the structure or we also use the content. Because imagine Facebook. Okay, if I create the graph and keep only the node and the link information, I lose important data about the user itself, about the content of its post or its profile. So what about if I also have the structure and also the content? So it's a huge a huge range of different things that I can find out about the network if besides the structure I have the content. So this is a general overview of the operations. Now, I have two examples of this kind of operation, just to give you an idea. One is offline, the other is online. The offline is a little bit technical, so stay with me. Okay, so let's start with the offline. The example of the offline example is about betweenness. Okay, as in life, the same thing happens with graphs. Not all things are equal. So not all nodes are equal. Some nodes are more important. So we want to find the most important, the central nodes in the graph. And there are many different definitions of what makes a graph a node important. For example, the degree is the natural thing that comes to mind. The more connections you have, the more friends you have, the more important you are. But there are other things like closeness. I will talk about betweenness in a while. Also page rank, I'll talk about it later. And then eigenvectors. Okay, what is betweenness tetradic? Here comes the mathematics. We have a node, and we want to count the number of shortest path that goes through this node. Okay. For example, here you have node 4, and node 4 is an important node because main shortest path goes for 4. It's easy to see it. All the nodes in the left of 4 to communicate with the nodes in the right of 4 have to go through 4. So 4 is a central node in the sense that many shortest paths goes to 4. So this is why we use betweenness, and there is a slight detail that we also want to count the different the number of different shortest paths. So because if you want to go for 7 to 4, there are two different ways to go for 7 to 4. You can go through 5 and through 6, right? Okay, so there are two shortest paths from 7 to 4. So you don't want to account to give all shortest path of 4 to 7 to 5. So you divide this number by the number of different shortest paths that go from 7 to 4. And that gives us this formula here. So the number of shortest paths divided by the different number of different numbers. Okay, so this is betweenness, and here is visually how it looks. The blue nodes are the central nodes in terms of betweenness, and the red ones are the less central. Nodes with high betweenness are important in communication and information diffusion. So one offline problem that offline type of analysis is how to compute between it. And I will give you an idea of how to do it. Now, betweenness is also a nice example because it's used in another type of offline analysis. It's graph partitioning. As I said, these graphs have small clusters on them. So one important offline thing that we do with graphs is try to cluster them and find densely connected subgraphs. I have two examples. One is how people that work in physics, who knows them anyway, but people in this audience, I mean, people who work in physics, they are divided in different sub-areas. Okay. And this is a very small graph, which is used very commonly in social networks because it's from an actual social network. There are guys, 34 guys that joined a karate club, and after a while they formed two groups, the pink and the red, the white one. And they are actual group. They are actual groups. I mean, they hang out together, so they consider friends. It's not something that came out of an algorithm. And it's a very small graph, but it's used very often because it's real. So there are two groups, one around the president and one around the instructor. So we want to find this kind of this is the kind of offline analysis. And there are many algorithms to do that. One uses betweenness, and not node betweenness, but as with nodes we can do the same with edges. So they use edge betweenness, which is the same concept as I described before. How many shortest paths pass through each edge? For example, for this edge, there are all the shortest path from these three, 1, 2, 3, all the shortest path from 1, 2, 3 to all other nodes in the network pass through 3, 7. And here we get an out for the other. Okay, so how does clustering works in this example? The betweenness of all nodes in the network are calculated. And then, then you find the node with the highest degree of betweenness. You remove it from the graph. You get two subgraphs. You repeat this process. You reevaluate betweenness, and then again remove the node with the highest degree, and so on. And here is how this works in this graph. Okay, this is the numbers, and then the highest is 7. And then you have the two subgraphs. Okay, one on the left and on the right. If you want to go further and further divide these subgraphs, you get something like that. Okay, and now this algorithm worked on this algorithm applied to the Karate Kid, gave these two networks. It actually managed to find the actual networks, but instead of just one node, node 9, which although it's smallly connected to the president of the club, because he was just 3 weeks away from getting a black belt, he hung out with the instructor. So that's life. Okay, so what's the take out of this? This is that I just wanted to show this example, and it goes on that analysis on these graphs can get complicated, and imagine doing that in very large graph. For example, to compute betweenness, to find all the shortest path, the only way to do it is to run BFSs. BFS, do you know BFS? Is best first search from a node. So you have to perform a BFS starting from each node, determine the shortest path from this node to all other, and then based on this number determine the amount of flow from equal other nodes, and then repeat that for all nodes in the graph. So this is very time-consuming, computational-consuming task. You cannot do it efficiently on large graphs, so you have to do something about it. Okay, now I have the details of how this works. I think I will skip them. Okay, I'll go first. Okay. Even faster, okay. So this is the initial network. This is the BFS from node A. I do one top-down traversal, a BFS. This is the initial graph. I run a BFS starting from A on this graph. Now I go top-down, computing the shortest path from A to other nodes. For example, from node A to K, there are 6 different shortest paths. from node A to F, there are two different shortest paths. And then I go bottom up, dividing the number of shortest paths I found with the number of different shortest paths. I saw an example. For example, for K, there are 6 different shortest paths. Half of them come from I, and half of them come from J. So, JK takes 3 out of 6 shortest path. That is, it has between us 1/2. And do that for all nodes. This is betweenness is one tough algorithm to run on huge graphs. But the nice thing about it is that it is parallelizable. You can do it easily in parallel. How? Run a different BFS from each node. But still, even if you do it in parallel, it's still very time consuming, and then randomization comes into place and it gets really complicated. Okay. So this is a form of offline analysis. If you have any questions or comments, please feel free. Or a better algorithm for betweenness. Okay, great. Now let's see about an online example. As I said, online in the case of online query process, online analysis, you have queries. You have the graph and you have queries. One of the simplest queries that you can ask is a reachability query. So you have a direct graph, you have 2 nodes, U and V, and the reachability query asks whether there is a path from U to V in the graph. There are 2 simple ways to do it. You can do online traversal. So you can start, you have the graph, you start from node. You do BFS or TFS, your favorite traversal, and then you either find V or you do not. So this is online traversal. The cost of online traversal, the query time of online traversals is ON and plus N. It's linear to the number of nodes and edges in the graph. But you do not have to do any pre-processing, no construction time required, you just do this online. No space required, extra space required. The other extreme way to do it is you have the graph, you do a full free processing. You compute reachability for all pairs of queries. Okay. This gives you an n square table, reachability table, that says which nodes connect to what node. Okay. Now, you can do query time on the fly. You just look up a table. So query time now is constant. Just look up. But you pay for the construction time to compute it, to construct the actual reachability. It's ONN. If you try to do reachability for even a moderate sized graph, it takes days. It's very time consuming. But if you do it, if you have the days, the months to compute it, you can do it. Okay, and then you have to store it. So if you have months and very large storage, you can do this, and you have constant time. Now there are of course always there are approaches in between these 2 extremes to do it anything offline, to do anything online. So here comes indexes. Okay. So you can, instead of storing the whole reachability, the whole transitive closure, you can do some compression or compute something less powerful than that. Okay, and there are various indexes that are proposed for reachability queries. Actually, there are various indexes proposed for many of these queries in large graphs. I'll show you an example. It's called 2-hop index. Okay, as a first step, these graphs can have cycles. Okay, so you don't want to have cycles in your graph. You find the strong connected component. So, for example, A, B, and C are all connected to each other. So, instead of maintaining information about A, B, and C, you cluster all them together. You replace them by a single node 1 on the right, and you do the same for all nodes that are connected. Okay, so now you don't have to have information about whether A, B, and C are connected. You know that they are connected because they belong to the same cluster. Okay, so first, step 1, you take the graph and you find the connected components, and you replace the original graph with a much smaller graph, recall that I said that there are clusters. Our graphs that come from natural networks are clustered. So this works very well in actual graphs because they are clustered by nature. Okay. So the second graph is really smaller than the original one. And then, okay, already we have saved some space. And the next step is, okay, instead of the transitive closure, the idea is to do some kind of compression. So in the transitive closure, for each node, we have the full list of the nodes that are reachable from it. Instead of that, we do what's called a two-hop code or label. So the idea is that for each node, we have two labels, two lists. We select a number of nodes that link to this node, called L-in, and a number of nodes that are reachable starting from this node, called L-out. And the idea is that if we can find, if we can ensure that for each pair of nodes that are reachable U and V, V is reachable from V if the in set to U and the out set of V have at least one node in common. Okay, sounds complicated, it's really simple. The idea is that if I have two nodes, instead of keeping the information, all the information, it's sufficient to find a single node, say W, and then have W in the in and out list of both. So if I can reach W coming out of U and in from V, then U and V are connected. Okay. So at least as far as I can find this node. Okay. So this is the idea of how these indexes work. Okay. You try to find to create smaller information, keep smaller information about each other. Okay. Okay. So there are. The point of this was to show you the variety of different things that we can do with graphs. Okay, we can use indexes, we can do online analytical processing, and the question now is, can we build just one system? There are two things that make graph data different than the data we know. One is it's pure locality. Because accessing the neighbors of a node requires jumping around. Okay. So it makes it very difficult to partition a graph. How can you partition a graph? This is a very tough problem because of traversals. There is no locality. The other thing is that data are structure driven. So computation is driven by the structure of the graph, much more than with regular data. So these are two tough things that we have to do to handle when it comes to graph data. Okay, so that was what, and now let's talk about how. How can we do this? Are there any tools or systems that work with graphs? Actually, there are many. So there are systems for non-graph data that we can use for graph data. They all good relational DBMS. There's manual systems, then there is MapReduce. We can use them to do graph. They may not work well, but we can use them. Okay. And then there are systems that are built in particular for graph data. And those are graph databases. And then there are MapReduce-like systems. And then there are systems that work on large graphs but have a different model. Okay. I have a couple of slides for each one of them. So you will learn more. Okay, so RDBMS. How do we store a graph in a relational database? Okay, there is a simple natural way to do it. So you have two tables, one table for nodes and one table for edges. Okay. So the first table, in the first table, let's call it vertex table. You save information about nodes. In the second table, the edge table, you keep all pairs of connected nodes. So one is connected to 2, 2 is connected to 6, and so on. Now, can you do traversals using this relational database system? You can, but how? Okay, you need to join. the neighbors of a specific node, you just need to join the vertex table with the edge table. But then if you want to find the neighbors of a neighbor, you need to do a second join of the edge table by the edge table itself. So to do traversals, you require multiple joins. So it pays. You can do it, but you need a lot of joins to do it. Okay, so we use relational database systems. They are there's widespread use of them. They have strong data guarantees. They support complex queries, and then they actually may be useful. So they may be useful when you have also structural content information and you want to figure out specific nodes with properties. But if you use them, you need to do joins. Can we use MapReduce? Do you know MapReduce? Great. The perfect audience for MapReduce. Okay, so it's a general purpose data processing platform optimized for online analytics on large data partition on hundreds of masses. Okay, so you can use MapReduce to do graphs. Actually, there are a lot of there are a number of implementations of graph algorithms MapReduce. There are two problems. One is that one is the user problem that I talked about. How do you partition the graph, which is a general problem. The other two things is that you need to store intermediate results of each direction. And the other thing is that you may need the entire graph structure to send over the network after each direction. Okay. Now there is a system in the Hadoop family called Pregel. Actually, it's a Pregel. But the idea behind the Pregel is to think like a vertex. So Pregel was introduced by Google, and then there are many open source implementations of Pregel. Giraffe is the one that is part of the Apache software. And the idea here is, okay, think like a vertex. What does this mean? Computation proceeds in super steps, and each super step, each vertex read messages sent in previous super steps, each vertex does some local computation, and then send messages. And this goes on. So you are a vertex, you get messages, you compute something, you send messages. And you do that in others. That's the simple idea behind Pregel and I have some animation here. So each vertex runs a user-defined program, and then you use messages and you send messages to other methods. Now there is also GraphLab, which is basically a similar model, but instead of using messages, you do it through shared state. So instead of receiving messages from your neighbors, you read, in simple terms, you read the memory of you share memory with the nodes close to you. Okay. And parallelism becomes natural because each vertex does this by its own. Receives messages, computes, sends messages, and this is repeated. I have a page run computation which I'm going to skip. Okay. So have you heard of PageRank? PageRank is a simple way to compute how important is a node based on how important your neighbors are. So this is a formula of how to do PageRank. PageRank is one of the basic offline computation that we do in graphs and the testbed for many of these platforms. So PageRank is a very natural thing to do. So at each step, each node receives messages from its neighbors. Use this information to update its PageRank and then send new messages to the other nodes. And this is repeated. And if you want to do it with shared memory, you look at the memory of your neighbors, you update your own value of your own PageRank network, and you trigger your neighbors with something that says so they can update their state. Okay, and this goes on, and how this process terminates. It's a vertex, thinks like a vertex, and decides to vote to halt. When all nodes have voted to halt, termination ends, and that's how it works. Okay, this is the implement. The basic. It has a basic architecture like magnitude. You have the master and you have the worker. The basic says how to do partition. I emphasize this. This is not easy. And then master assigns the subgraph to its worker. Super steps begin at its worker. Its worker gets some nodes, in this case, and computation procedure. Okay. Okay. Now the Brekel-like parallelism is a form of bulk synchronous model. We have fine-grained parallelism at the node level. So we have parallelism at the node level, which is very fine-grained. Does not move graph partitions over the network, but it's not appropriate for many graph algorithms because of the fact that it doesn't support easily how to save storage. For example, betweenness is very tough to do in Brekel. There's no, or giraffe in any of the systems, there's no well-known implementation of betweenness using such systems. It's very difficult. Now there is another approach to do this kind of stuff. It's called Pegasus from CMU. It's again an open source large graph mining system, again implementing on Hadoop. The idea in Pegasus is quite different. For Pegasus, everything is a matrix. So all graph mining operations are converted into iterative matrix vector multiplication, everything. Okay. So they try to do everything through matrix multiplication. Okay, so you have the graph, and you all know the adjacency matrix. So instead of the graph, you maintain the adjacency matrix of the graph. You also normalize it, normalize it. So the columns sum up to 1, and this is how you present the graph. Just a matrix. And then you have vectors that represent some value of the nodes, like page rank, and so on. Now the idea is to have core operations that correspond to matrix multiplication. And here is the matrix vector multiplication of the matrix to represent the graph and any vector v. To do matrix multiplications, you multiply each row with the vector, and then you sum up all the values, and then you assign a new value to the vector. Okay, so that's what Brekel does. Brekel defines 3 basic operations. Combine 2, which is just the multiplication of the cell with Bj. Combine all, with just the summation, and assign. And the idea is use these 3, customize these 3 basic operations, and do any graph operation you want using this. Okay, page rank is easy to do. So the basic idea is use assign, combine, and combine all, and this is called the xj operator, and you try to do anything using this xj operator, customizing assign, combine all, and combine two. This is applied till the convention continuously, and the difficult thing is how to customize this function. Of course, you can, if you spend a little bit of time, you can think how to do page rank using this. Because page rank is basically matrix multiplication. Okay. So this is the formula that gives us page rank, and this is how to do it using combine to combine all and assign. But can you do anything with matrices? You can do many things, but not all things. For example, the creators of PageRank and many of Pegasus, of this system, and others have implemented various algorithms using Pegasus. For example, you can find connect components. For example, take this graph on the left. So you have 2 components, A, B, and C, and you want to do it, to find them using Pegasus. It sounds so difficult, but there is a simple idea that can help you do it. The idea is that the following. Okay, so you know that 1, 2, 3, you want to have as output that 1, 2, 3, and 4 belong to cluster A, to component A, 5, 6 belong to component B, and 7, 8 to component C. Okay, if instead of this information you just keep, you don't name the clusters, but you just name them by the node with the smallest ID. So cluster A is cluster 1, cluster B is cluster 5, and cluster C is cluster 7. By making the simple assumption, you can find a nice multiplication algorithm to do it. And the idea is that, okay, so now your output is not it's not A, B, C, but clusters A, clusters 1, 5, and 7. And what we want to do is to find how to combine the adjacency matrix with this information and get the final vector. The idea is the following. It's at each direction, you send your ID to your neighbors, and you keep the smallest among your ID and the ID of your neighbors. And you do this at each convergence. And this gives you the cluster. So I had this example to show that although matrix multiplication seems a little bit limited, you can do some things with it. So this is Pegasus, excuse me, which is a matrix-based graph mining platform. It supports large-scale graphs. Many graph operations cannot be bought, but many graph operations cannot be modeled by matrix vector multiplication. Many can, but many cannot. And of course, it's not very natural. When we think about graphs, most of us do not think about matrix multiplication. Most of us, with very few exceptions. Okay. Now let's go to databases, and this is the last system that I'm going to talk about. So we have graph databases. This databases have a different model than relational databases. Their model is a graph. It's a property graph. It contains nodes and directed edges. Nodes represent entities, edges represent relationships, and both node and edges have properties, which is basically key-value pairs. The basic operation is not SQL, it's traversal. So the basic operation supported by a graph database is traversal. You start from a given node, you explore portions of the graph based on some query. For example, typical queries that we can make to such databases is who are the friends of friends of friends. AB, what is the average rating for a given movie given by users? Friendship distance for me is at most 5 hours. So there are many graph databases out there. One popular one is Neo4j. It's an open source graph database, and Cypher is its query language. So Neo follows. Here is the stack is okay. Now it follows the property graph model. So that you have nodes which have properties, and you have links that have properties as well. And Cypher is the query language. The basic operation of Cypher is traversal. So you start from a node, you follow links that satisfy a given pattern, and you have a return expression that says which sets of nodes you want to treat it. Of course, I'm not going to teach you Cypher, just an example. So here is an example of a simple Cypher query. You start from a node, and then you follow links that match a specific pattern, and you return and specify which nodes you want to return. So that's the basic idea. You follow links that satisfy a pattern, and you also can express patterns using the properties not only of links, but also of nodes. And then we can do path, name path, and so on. Okay, so graph database have a power data model, they're fast to connected data, but again they have a problem with how to do partitioning and how to do distribution. Sharding is a new name for distribution, so distribution on key value, and it's very hard to do. It doesn't work here, and so to do efficient query processing on Neo, you need to cache a lot. You need to find ways to have a lot of information in memory if you want to do efficiently anything. Otherwise, you end up using a lot. You have a lot of random access, and you end up using a lot. That is. Okay, so to wrap up with systems, there is no consensus on a single model. Partition is a big issue. There are many systems that follow one or the other approach. So there is no consensus on what is the best way to, what is the best system to use to solve a data graph problem. Okay, okay. So this is this is the end of this tutorial almost. I have just one slide representing our own work. So we do work on graphs. Actually, we work on graph evolution, something that we didn't touch in this tutorial. So these graphs evolve over time, and what we do is we want to find a way to query the graph history, to do indexes to query the graph history. For example, which were my friends in 10 years ago, or what was I doing some years ago. So we want to build indexes to give the history of graphs. And the other thing we are working on is diffusion, something I didn't talk about also, of how information propagates on evolving graphs. This is the two things we are working on. Okay, so summary. Why, what, and how? Why use graphs? Because graphs are everywhere, they're ubiquitous. Then there are many useful applications. Hopefully I show you some of them. I've shown you some of them. What kind of analysis can we do? There's a great variety of problems that we can look on for both online and offline analysis. How? There are many graph-oriented parallel processing systems and databases, but there is still a lot to be done. Nobody knows which is the best system yet. Okay, so what is the take-away message? It's a very active area of research, many research problems, many opportunities for most computer science fields, and since you are a service-oriented audience, many problems for you to think about. Can we have graphs, let's say, as some kind as a service or something that the users can get out of for simpler terms than writing their own algorithm. Okay, so that's the end of my talk.
Yes, thank you.
Excuse me if I was a bit fast. I didn't overwhelm you with too much information.
It's my audience, so I'm sure they did everything.
Okay, that's nice.
So perfect timing. We have a few more minutes for questions. And let me just first say that students who are interested in finding a good topic, this is obviously a very hot area, feel free to talk to Professor Pitoura about
sure.
Opportunities.
I love talking with people about research, so feel free to send me email. I don't have my email.
Okay, there's one question there.
Excuse me. Facebook is also, they have introduced a new feature, graph search.
Mm-hmm.
So how they are doing it? Are they using relational databases at the back end?
It's actually it's embarrassing, but they use a combination of things. So initially they used MySQL, they used part of it is MySQL, another part of it is their own graph databases. So they use a combination of tools, not just relational or just graph. There is a paper, if you can look it up, which explains how research is done in Facebook. Last 6 months, I think. So I can send you the reference. But it's not, the point is that it's not a single system. They started with MySQL, it didn't scale well, so they start adding things to it. So they're using a combination of MySQL and their own graph-based system.
There is the area of linked open data, and I guess you mentioned it when you have shown the network, the semantic network kind of thing. What are they heading to at the moment in organizing that data and the information?
Actually, I'm not into that area that much, so I'm not sure that I'm the right person to answer this question. I think the emphasis also on the semantic part the general idea is how to find a way to match things that refer to the same entity. So there's a lot of work being done for semantics or ontologies on how to identify relations about things and do more knowledge-based process. They tend to use RDF as well. So it's graph, but it's a special type of graph.
But there is a very efficient RDF processing already on relational data stores, right?
Yeah. Actually, there is a
the triple store.
Yeah, you are right. There is there is a big argument on whether you can relational databases are better than graph databases. So there are a few papers out discussing the performance of the graph database vs relational database. Relational database, even if they use joins, but still they are more efficient sometimes than graph database. I guess not hundreds, but decades of work on query processing pays out here. So it's not clear whether a graph. What makes things even harder is that there is no, let's say, a benchmark. So there is not a benchmark that you can run it and say which one is best, which system is best.
When you consider this Prägel system, you mentioned this system where you consider networks of processes,
Okay.
and then you say each process alone, each node eventually terminates. And then you said, okay, the whole algorithm terminates if each node has terminated.
That's the model.
Okay. But the question would be, in case it has terminated, the whole system terminated, who knows that the whole system has terminated?
Oh, I guess there is a coordinator who gets a whole view of the system. So there is a coordinator that checks that.
Okay, but it's not so trivial for the coordinator to recognize the last node has already happened.
Well, I'm not the Prägel expert, but I guess they have an efficient way to do it. I can think out of my head of ways to do it, but I'm not sure how exactly they do it. But there is a coordinator, there is coordination.
So maybe you can have one more question.
You mentioned the last slide, the graph service.
Oh, that's, speculative, okay.
How do you envision it? Who can be the end users and what can be used for? I mean, other than just querying graphs and finding the best nodes.
Actually, there are many applications. For example, someone who wants to create recommendations. So if you want to do recommendations, you have to use the graph. So if you could provide somehow a traversal as a service or something like that, a guy who works on recommendations will use your graph traversal service to work on recommendations or to do some analysis for marketing, how something spreads in the network. So there are applications. But but my point is that the abstractions are missing. So we don't have the abstractions.
Any further questions? Okay, so we'll break for lunch. Enjoy your lunch. Let's thank the speaker again.